Hi, so you're probably finding this video thinking, oh hey, this guy might be able to help me out with the logic behind linear interpolation. Have no fear, I will explain it. I'm going to explain it to you in a way that I found quite intuitive. The way professors explained it to me when I was in college, I found it didn't really make sense in my mind, mainly because I'd been out of school for quite a few years before I went to college. But after doing it a lot, I've wrapped my mind around it, and if you're successful in your undergrad, you probably won't even need to see this. You'll probably figure it out pretty fast. But if this is a help to you, so be it. So I made up this example problem. I don't even know if it's practical. I just grabbed a table. I was like, oh, temperature, pressure. I know they're related. Maybe we can make some sort of correlation. So what these are the pressures at which the phase changes will occur in water at different temperatures. And what I'm asking is, okay, so we know at 12 kPa, we know at 15 kPa, plus some change, what temperatures the phase change will occur. What if we control their pressure so that we have 13 kPa? What temperature is the phase going to change at? And I don't know any practical uses of this, but hey, it's good for the example anyways. And it's all we really need to know. So when we do a linear interpolation problem, we need to know the assumptions that we're making first off. So before we even look at this problem and how to solve it, let's wrap our mind around what linear interpolation is. So we have some function. We don't know what that function is. And I'm going to call it f of x just for simplicity's sake, consistency's sake with everything else we've seen. So that would make this our x-axis and this would make this our y-axis. Or you can even write f of x up here as our dependent variable, and this is our independent variable, and that's going to come into play in a little bit. So what we're doing is, with the table, we don't know what this function is, but we do know that these points land on this function. So what we're doing is we are assuming between these points we have straight lines as opposed to a curve. Now, in some cases, this is going to result in significant error, but in a lot of cases, especially the design tables that say, hey, find intermediate values using linear interpolation, they've already done the math to find out that the error is minimal, and it's probably a lot faster than actually programming the huge function that they use to get those numbers. Because in a lot of cases, they're using things like Gaussian distributions and stuff like that, which are just nasty formulas and usually have to be solved using advanced numerical techniques. So now, how do we estimate the equation of a straight line? We know the equation of a straight line is y is equal to mx plus b. That is a really ugly y. I apologize because I'm Canadian. And m is the slope of the line, which I'll write up here for you because it's going to come in real handy for us. y2 minus y1 divided by x2 minus x1, where x1, y1, and x2, y2 are 2 points on that line. And it doesn't matter where those points are, how close together they are, how far apart they are. When it comes to lines, that is always the slope. If it's a straight line, always. So right here, if we look at this, we got four numbers here. We can plug that in for m. We can get our slope real easy. That's not the hard part about linear interpolation. How do we know what our y-intercept is if we're predicting all these as straight lines? Like if we look at these 2 points, our y-intercept is going to come somewhere here. These 2 points, if we extend it down, oh, these are not very straight lines. And if I look at these 2 points, my y-intercept is going to be here. They're all over the place. Where's my y-intercept? That's really what's going to be challenging. And there's a trick. There's a trick to fixing that. Don't worry about that. So, and I'm going to show you that trick by solving this example. I've already explained the example to you. So what's our independent variable? That's going to be our pressure. Let's draw that right down here. What's our dependent variable? That's going to be our temperature. Off the top of my head, I can't recall what these graphs look like, but I don't need to. I'm just going to draw a random graph, and I'm going to call this my x1 point, and I'm going to use the lower numbers. I don't need to use the lower numbers. I can use either numbers. It doesn't really matter. The only thing that will change is my y-intercept obviously will change, and my x will change, and I'll show you why in a second. So this is 12, and this is 15. Oh yeah, that's also something else. It said we didn't know our x, but we had this number here, but that's not quite our x. It'll be close. Well, I'll show you why, because I'm going to employ this little trick. So we got 12, we got 15, put 50 here and 55 here. That is a really ugly 55. Alright. So I'm going to call this my y2, x2 point. We've already been over that. And I'm going to call this my y1. Why am I putting y's first? X's first. Come on, Andrew. x2, y2, x1, y1. And right here at 13, what we're really interested in, I'm going to call that xc. That is not a c, yc. In order to derive the equation that I'm going to show you that'll work for any linear interpolation problem. So let's plug what we know into what we know already. So we know, actually let's get some space going here. We know our yc right here is going to be equal to y2 minus y1, where we have all those numbers. You know what? I'm going to switch pens because this is important. Yc, oh that's nice, is equal to y2 minus y1 divided by x2 minus x1. Now before moving on into the x and the b, remember I said, we don't know what our y-intercept is. We can force it to be either 50 or 55 by redefining an axis right here. Or if we can define it there as well. But I'm going to define it here because that's what I have memorized, and that's just the way it works with me intuitively. You can define it here. Your math just changes a little bit, not too much. So our x value is no longer 13. It's going to be 13 minus 12 and change, right? So 13 corresponds to xc, and 12 is x1. That's the big trick in getting this x value. And now we know our y-intercept when x is equal to 0, in this case 12, but it's just we've shifted our axis over in our new coordinate system. Y is equal to b. So y is going to equal 50, or b is going to equal 50. So we just add y1 on. And this formula right here will work for any linear interpolation you do. It doesn't matter which direction it's going in. Is it a positive slope, a negative slope? That gets sorted out in your m right here, your y2 minus y1 divided by x2 minus x1. You just have to be careful about this right here, xc minus x1 plus y1. Or if you set it up here, your x value now is going to be x2 minus xc. Be very careful about that. It gets reversed, right? And then your y value would be y2. So you just have to pay attention to what you're doing. If you need to draw a picture the first few times, I recommend doing that. That's always helped me out when I'm struggling in engineering. I just draw something, and it typically helps me out a lot. Like, oh, hey, I can see what's going on quite a bit. And in math, the same sort of principle applies. So let's solve the problem now that we got our formula. We can just plug and chug, right? So we know our yc, in this case, is actually a TC, I guess, temperature in degrees Celsius, is going to equal 55 minus 50 divided by 15.763 minus 12.352 multiplied by 13 minus 12.352 plus 50. And if you give me a second, I will calculate that out for you. Oh, it is 50.95. Boom. So YC, or our temperature in degrees Celsius, is equal to 50.95 degrees Celsius. So I think I'm going to type this formula into the description if it helps. And yeah, thank you very much. I hope this has been a huge help to you